The lights were too faint to be seen by human eyes. They did not resemble the glow of a city, nor did they flash like a signal or spell out a message from another world. Instead, they were far quieter than that. A tiny pattern hidden in the darkness, a weak glow from a distant planet, and a strange trace of light appearing where no light should have been easy to explain. At first, scientists assumed it was nothing more than noise. Then they considered that it might be a reflection. But as the data was examined more carefully by the James Webb Space Telescope, another possibility slowly began to emerge. An uncomfortable question took shape. What if the darkness on that distant planet was not completely dark? For centuries, humanity has looked into the night sky and asked the same timeless question. Are we alone? It is one of the oldest questions our species has ever asked, older than telescopes, rockets, radio signals, and space probes. For most of human history, the answer belonged to philosophers, dreamers, and anyone who stood beneath the stars wondering what might exist beyond them. Today, however, that question belongs to science. We now know something our ancestors could only imagine. The stars are not simply distant points of light. Many of them have planets. Some of those planets are rocky. Some may possess atmospheres, and others may even contain vast oceans. Some orbit within regions where temperatures could allow liquid water to exist. The universe is no longer just a silent ceiling above us. It is a place filled with countless worlds. The James Webb Space Telescope was built to study those worlds in ways no telescope had ever achieved before. Webb can analyze the faint light from distant planets, examine their atmospheres, search for chemical signatures, and separate incredibly weak planetary signals from the overwhelming brightness of their host stars. Yet among all the possible discoveries it could make, one type of signal would change everything. Not oxygen, methane, or water vapor, but artificial light. Imagine a faint glow on the dark side of a distant planet, a sign that something there is not only alive, but building, organizing, using energy, and transforming its environment. That possibility is what makes this discovery feel so unsettling. Detecting light on a distant world is already extraordinarily difficult, but detecting light where no obvious natural explanation exists raises a far deeper mystery. Planets can shine for many natural reasons. They reflect the light of their stars, radiate heat, produce storms, generate auroras, and display changing patterns caused by clouds, ice, volcanic activity, or atmospheric chemistry. Nearly every unusual light observed in space eventually receives a natural explanation, and scientists always begin their investigations there because they must. Scientific discovery depends on eliminating ordinary possibilities before considering extraordinary ones. But if a faint pattern of light repeatedly appears on the dark side of a planet, if it shifts, repeats, or behaves differently from ordinary reflected starlight, the question becomes impossible to ignore. Are we seeing a storm, a volcano, an aurora, an unusual reflection, an error in the data, or something far more difficult to say aloud? The stakes could not be higher. The first evidence of another civilization may not arrive as a radio message, a spacecraft, or a dramatic signal intentionally directed toward Earth. It could simply be a faint, distant glow from the night side of a world so remote that its light has traveled across space for years before finally reaching our telescopes. If James Webb were ever to detect something like that, it would not simply represent another astronomical observation. It would mark the moment when one of humanity's greatest questions became measurable, not through belief or imagination, but through scientific data. Hidden within that tiny pattern of light could be the first clue that another world has learned to transform darkness into light. To understand why such lights would matter so much, we first need to appreciate how incredibly difficult it is to observe planets beyond our own solar system. A distant planet does not shine like a star. It is small, faint, and usually lost within the blinding glare of its parent sun. Studying an exoplanet is often compared to trying to spot a single candle sitting beside a lighthouse from miles away. The star dominates nearly everything. Its light floods the telescope, its heat overwhelms the system, and its immense brightness hides the planet almost completely. Yet astronomers have developed remarkable techniques to discover these hidden worlds. Sometimes they detect a tiny dip in a star's brightness as a planet passes in front of it, a method known as the transit technique. Other times they measure the slight wobble of a star caused by the gravitational pull of an orbiting planet. In rare cases, they can even separate the planet's own faint light from the brilliant glow of its star. Finding an exoplanet, however, is only the beginning. Studying it presents an entirely different challenge. Scientists are not looking directly at oceans, mountains, or drifting clouds. They are certainly not watching city lights flicker on at night as we might see from orbit around Earth. Instead, they work with incredibly small changes in light, a slight dip in brightness, a subtle shift in color, or a faint spectral signature buried within the overwhelming light of the host star. This is where the James Webb Space Telescope becomes so important. Webb was specifically designed to detect infrared light with extraordinary sensitivity. Infrared observations can reveal heat, atmospheric chemistry, and extremely faint signals that older telescopes struggled to capture. When a planet passes in front of its star, a small portion of the starlight filters through the planet's atmosphere before reaching the telescope. Different molecules absorb different wavelengths of that light, leaving behind a unique chemical fingerprint. By studying those fingerprints, scientists can search for water vapor, methane, carbon dioxide, and many other gases that reveal the composition of distant atmospheres. But light can also tell a very different story.